Our next topic is polynomial congruence modulo P and Lagrange's theorem. It's an important section, so we start with the Lagrange's theorem. The statement is given a prime P, let f of x equal to the polynomial of the form c0 plus c1x plus c2x square plus etc. cnx power n with the degree n and integer coefficients such that cn not congruent to 0 mod p, that is p does not divide the leading coefficient cn. Then if we consider the congruence f of x congruent to 0 mod p, then it has at most n solution. We have to show that if these conditions are holds, and then the congruence f of x congruent to 0 mod p has at most n solution. So we use induction on n to prove this theorem. We start with n equal to 1. Then f of x can be taken as f of x equal to c0 plus c1x, and where p does not divide c1. Then we have to consider the congruence f of x congruent to 0 mod p. We have to show that it has at most one solution, that is it has only one solution, or it has only unique solution. So consider the congruence f of x congruent to 0 mod p. That implies c0 plus c1x congruent to 0 modulo p, or we can rewritten it as c1x congruent to negative c0 modulo p. And given that p does not divide c1, that means GCD of p and c1 is nothing but 1. And then there is a theorem. The statement is if GCD of AM is 1, then the linear congruence AX congruent to B mod M has a unique solution. We know this theorem, it's a well-known theorem. So we use this theorem here, given that GCD of P and C1 is 1, therefore the congruence C1x congruent to negative C0 modulo P has a unique solution. There is only one solution. Therefore the result is true for n equal to 1. So we assume that since the result is true for n equal to 1, we assume that the result holds for all the polynomial with the degree n minus 1. So if we take a polynomial fx equal to c0 plus c1x plus etc. plus cn minus 1 x power n minus 1 with the p does not divide cn minus 1, then the congruence f of x congruent to 0 mod p has at most n minus 1 solutions. We assume this condition. So now we have to prove that the result holds for n also, that is if we take a polynomial with a degree n and with this condition, then this congruence has at most n solution. So by using induction hypothesis, the result holds for n equal to 1, and we assume the result holds for n minus 1 also. So we have to prove the result for n. So we consider a polynomial with a degree n, f of x equal to c0 plus c1x plus etc. plus cn x power n with the p does not divide n. And we have to show that the polynomial congruence has f of x congruent to 0 mod p has n at most n solution. So we assume that this congruence has more than an incongruent solution. We assume this condition, more than n solution, incongruent solution, and let it be x0, x1, x2, etc. xn, that is here it is n plus 1 number total. So x0 satisfies this condition, x1 satisfies this condition, x2 satisfies this condition, etc. xn also satisfies this condition, and all are incongruent. So here we take more than n distinct or incongruent solution. So finally we have to get a contradiction. Then we consider the equation f of x minus f of x0. f of x minus f of x0 is nothing but c1 into x minus x0 plus c2 into x square minus x0 square plus etc. plus cn into x raised to n minus x0 raised to n. Here x minus x0 is a common factor in all these terms, so we can take x minus x naught outside. So we'll get x minus x naught into a polynomial of degree n minus 1. This degree of g of x is n minus 1 with the leading coefficient. We take x minus x naught all outside from all these terms. So finally here it's a term of n power n minus 1. So finally we will get a polynomial of degree. G of x is a polynomial of degree n minus 1 with the leading coefficient is Cn and p does not divide Cn. So we can use induction hypothesis here. That is, g of x has at most n minus 1 distinct solutions. By induction hypothesis, g of x has at most n minus 1 distinct solutions. So we consider for k equal to 0, 1, 2, etc. n, we consider f of xk minus f of x naught. F of xk minus f of x naught is nothing but xk minus x naught into g of xk. Sorry, not 0, fk equal to 1 to etc. n, g of xk minus f of xk minus f of x naught equal to xk minus x naught into g of xk. Since f of xk is congruent to 0 mod p, because x0, x1, x2, etc. xk are incongruent solutions of f of x congruent to 0 mod p. Therefore, each xk satisfies this condition. Therefore, f of xk is always congruent to 0 mod p, and here x0 is also a solution. Therefore, f of x0 is also congruent to 0 modulo p. Therefore, we will get left side is congruent to 0 mod p. Therefore, right side will also congruent to 0 mod p. Therefore, we will get xk minus x naught into g of x congruent to 0 mod p. From this we will get, this is g of xk, g of xk congruent to 0 mod p. Because xk minus x naught is not congruent to 0 mod p, since k varies from 1 to n, and here x naught, therefore xk minus x naught is not congruent to 0 mod p. Therefore only g of xk is congruent to 0 mod p, where k varies from 1, 2, 3, etc. n. That is, g of x congruent to 0 mod p has n solutions. Here these all k values, k varies from 1 to etc. n satisfies this condition, that is x1, x2, etc. xn satisfies the congruence g of x congruent to 0 mod p. But we already told that g of x congruent to 0 mod p has at most n minus 1 solution. This is the only possibility. Here we will get it has more than n minus 1 solution, which is a contradiction. This is because we assume that f of x congruent to 0 mod p has more than an incongruent solution. Therefore, we can say that f of x congruent to 0 mod p also has at most n solution. Therefore, the result holds for n also. Hence, the result holds for every integer. This is the proof of Lagrange's theorem. Is if f of x equal to c0 plus c1x plus etc. plus cn x power n is a polynomial of degree n with the integer coefficient, and if the congruence f of x congruent to 0 mod p has more than n solution, then every coefficient of f is divisible by p. In Lagrange's theorem, the statement is if f of x equal to c0 plus c1x plus etc. plus cn x raised to n, if and with p does not divide cn, then this congruence has at most n solution. Here this condition is not given, and here the statement is if f of x congruent to 0 mod p has more than n solution, then every coefficient is divisible by p, that is p divides c0, p divides c1, etc. p divides cn. We have to prove this. So we assume that up to this condition holds. That is, f of x is a polynomial with the integer coefficient and this congruence has more than n solution. We have to show that this condition. So we assume there are some coefficients that are not divisible by p. There exist some of the coefficient such that p does not divide that coefficient, and let ck be the largest one, ck be the one with the largest index, that is p does not divide ck, but after that all the coefficient is divisible by p, that is p divides ck plus 1, p divides ck plus 2, etc. p divides cn. So this is the one with the largest index. So we take g of x as, we split the polynomial up to ck and ck plus 1. So g of x equal to c0 plus c1x plus c2x square plus etc. plus ck x power k with p does not divide ck, and h of x is the polynomial ck plus 1 x power k plus 1 plus etc. plus cn x power n. Then f of x become g of x plus h of x. Then f of x becomes g of x plus h of x. Now we consider the congruence g of x congruent to 0 modulo p. We can use Lagrange's theorem here because the statement is of the form Lagrange. The statement satisfies the condition for Lagrange's theorem, that is g of x equal to c0 plus c1x plus etc. plus ck x power k with the p does not divide the leading coefficient p ck. Then this congruence has at most k solution. Therefore, this congruence has at most k distinct incongruent solutions. Now consider the coefficient h of x congruent. So consider the congruence h of x congruent to 0 modulo p. Here given that p divides ck plus 1, p divides ck plus 2, etc. p divides cn. Therefore, every integer is a solution of this congruence. Therefore, h of x congruent to 0 mod p has more than n solution, or every integer satisfies the congruence h of x congruent to 0 mod p, that is if you take any number here, h of 1, h of 2, h of 3, if you put any number here, p divides that polynomial, because p divides each of the coefficients ck plus 1, ck plus 2, etc. cn. Therefore, we can say that every integer satisfies h of x congruent to 0 mod p. Here g of x congruent to 0 mod p has at most k solution, but h of x congruent to 0 mod p has many solutions because every integer satisfies the condition. Now we consider the congruence f of x congruent to 0 mod p. H of x congruent to 0 mod p, we consider this condition, and instead of h of x, f of x we can rewritten as g of x plus h of x. G of x plus h of x equal to f of x. And given that, we assume that f of x congruent to 0 mod p has more than an incongruent solution. That implies g of x plus h of x congruent to 0 mod p has more than n incongruent solution, more than n solution. From this case, we can say that g of x congruent to 0 mod p has more than n solution. This is because we assume in the statement, we assume that f of x congruent to 0 mod p has more than n solution, and f of x is nothing but g of x plus h of x. Therefore, g of x plus h of x congruent to 0 mod p has more than n solution. Here already h of x has more than n solution. Therefore, the sum of these polynomials congruent to 0 mod p has more than n incongruent solutions means g of x congruent to 0 mod p has more than n solution. But we know that g of x congruent to 0 mod p has at most k distinct solution, which is a contradiction. Therefore, our assumption is wrong, that is every coefficient is divisible by p. This is the proof of this theorem. So we move on to next theorem, that is for any prime p, all the coefficients of the polynomial f of x equal to x minus 1 into x minus 2 into etc. x minus p plus 1 minus x power p minus 1 plus 1 are divisible by p. That is, f of x is nothing but x minus 1 into x minus 2 into etc. x minus p minus 1 minus x power p minus 1 minus 1. This is f of x. So we have to prove that every coefficient is divisible by p. So we take up to this as g of x. Take g of x equal to x minus 1 into x minus 2 into etc. x minus p minus 1. Then g of x congruent to 0 mod p has how many solution? P minus 1 solution, that is g of 1 equal to 0, g of 2 equal to 0, g of 3 equal to 0, etc. g of p minus 1 equal to 0. In general, g of I equal to 0 for all I equal to 1, 2, 3, etc. p minus 1. That is, if we put x equal to 1, g of 1 is 0, x equal to 2, g of 2 is 0, etc. x equal to p minus 1, then g of p minus 1 is also 0. Therefore, g of I equal to 0 for every I equal to 1 to etc. p minus 1. And we have GCD of I and p is equal to 1. That is, I varies from 1 to etc. p minus 1. 1 to p minus 1 and p is a prime. That is, every number less than a prime number is always incongruent or relatively prime to p. Therefore, GCD of I and p is 1. Then by Euler-Fermat's theorem, we can say that I raised to phi of p is congruent to 1 mod p. We can use Euler-Fermat's theorem, that is, I raised to phi of p is nothing but I raised to p minus 1 congruent to 1 modulo p. So instead of I, we can put it as x, that is x power p minus 1 congruent to 1 mod p. Or we can say that x power p minus 1 minus 1 is congruent to 0 modulo p. Or we can say that p divides x power p minus 1 minus 1. Or we can say that we can say that p divide x raised to p minus 1 minus 1. Okay. Now consider the congruence f of x congruent to, consider the polynomial f of x. Then f of x is nothing but g of x minus x raised to p minus 1 minus 1, which is congruent to 0 modulo p for every integer 1, 2, etc. x equal to 1, 2, etc. p minus 1. That implies f of x congruent to 0 mod p for every integer x equal to 1 to etc. p minus 1. So here we will get f of x congruent to 0 mod p has how many solutions? P minus 1 distinct solutions. That is, 1 satisfies the congruence, 2 satisfies the congruence, 3 satisfies the congruence, etc. p minus 1 also satisfies the congruence. Therefore, f of x congruent to 0 mod p has at most p minus 1 distinct solution. P minus 1 distinct solution. But let's see what is the degree of f of x. Degree of f of x is p minus 2. Because if we expand this equation, expand this polynomial, we will get x power p minus 1 minus etc. Finally, you will get x power p minus 1 minus 1. So we can cancel x power p minus 1 and x power p minus 1. Therefore, degree of f of x is p minus 2. Here, degree of f of x is p minus 2. But this polynomial congruence f of x congruent to 0 mod p has more than p minus 2 solution. Therefore, we can use the previous theorem. If this congruence has more than p minus 2 solution, then every coefficient is divisible by p. That is, p divides each of the coefficient of the polynomial. This is the proof of this theorem. So we move on to next theorem, that is Wilson's theorem. For any prime p, we have p minus 1 factorial congruent to negative 1 modulo p. So we take p equal to 2, first even prime number. Then if we take p equal to 2, then p minus 1 factorial is nothing but 1 factorial. 1 factorial is 1, and consider this congruence p minus 1 factorial congruent to negative 1 mod p, that is 1 congruent to negative 1 mod 2. This condition is always holds, that is 2 divides 2, therefore for p equal to 2 the results holds. So we consider the odd prime. This is 2 is the first only even prime number, so we consider odd prime numbers 3, 5, 7, etc. Then we use the previous theorem. We know that by the previous theorem, polynomial x minus 1 into x minus 2 into etc. x minus p minus 1 minus x power p minus 1 plus 1 are divisible by, all the coefficient of this are divisible by p. Every coefficient of this polynomial is divisible by p. Therefore, if we expand this, then we can say that the constant term is also divisible by p, that is p divides the constant term. Then what is the constant term? That is p divides constant term is 1 into 2 into 3 into etc. p minus 1 plus 1. This is the constant term. That is 1 into 2 into 3 into etc. p minus 1. Then there is a 1 here, that is plus 1. Therefore, we will get p divides, this is p minus 1 factorial, p minus 1 factorial plus 1, that is p minus 1 factorial plus 1 is congruent to 0 modulo p. That implies p minus 1 factorial congruent to negative 1 modulo p. This is the proof of this theorem.